You've come this far, 75 questions behind you, knowledge and confidence built step by step. Now the journey reaches its final stage. In part 4, we take on the last 25 questions. The toughest, the most defining, the ones that prepare you for victory. This is where preparation turns into mastery, and mastery opens doors. Let's finish strong. How does temperature affect output diversity in LLMs? Temperature is a hyperparameter that controls how deterministic or creative an LLM's output is during sampling from its probability distribution over tokens. Mathematically, before softmax, we divide the logits by the temperature Tt, low temperature, T less than 1, T less than 1. The probability distribution becomes sharper, so the model strongly favors the most likely tokens. Output, more deterministic, consistent, and factual, but less diverse. High temperature, T greater than 1. The distribution flattens, making less likely tokens more competitive. Output, more diverse, creative, and unexpected, but higher risk of incoherence or factual errors. In practice, for factual Q&A or summarization, I set T approximately 0.2 to 0.5 T to reduce randomness. For creative writing, brainstorming, or generating multiple ideas, I raise TT to 0.8 to 1.2. Example is if the top token probability is 0.9 and TT is very low, it will almost always be chosen, leading to repetitive phrasing. If TT is high, even a token with 0.05 probability might get selected, increasing variety but possibly lowering quality. What is a latent diffusion model? A latent diffusion model, LDM, is a type of generative model that applies the diffusion process, progressive noise addition and denoising, not directly in pixel space, but in a lower dimensional latent space learned by an autoencoder. How it works. 1. Compression. A pre-trained variational autoencoder, VAE, encodes high-dimensional images into a compact latent representation. 2. Diffusion in latent space. Noise is gradually added to these latent vectors over multiple steps. The model, usually a UNet, learns to reverse this process step by step to recover the clean latent. 3. Decoding. The denoised latent is passed back through the VAE decoder to produce the final high-resolution image. Why latent space? It's much smaller than pixel space, so diffusion training is faster and less resource-intensive. Latent representations capture the semantic structure of the image, allowing the model to focus on meaningful patterns rather than raw pixels. Example is stable diffusion is an LDM. It uses a VAE to map 512 by 512, 512 by 512 images into a 64 by 64 by 4 latent space, runs the diffusion process there, and then decodes back to the image. How can you interpret the hidden states of a transformer model? Interpreting hidden states in a transformer means figuring out what each layer's internal representations are capturing from low-level syntax to high-level semantics. Recommended approaches are 1. Probing classifiers train small classifiers on frozen hidden states to test if they encode specific features, e.g. part of speech, sentiment, entity type. If a layer's states predict a feature well, it suggests the model encodes that information there. 2. Attention pattern analysis. Visualize attention weights to see which tokens attend to which, can reveal syntactic dependencies, coreference resolution, or reasoning chains. Third dimensionality reduction and visualization. Use PCA, TSNE, or UMAP to project hidden states into 2D and check if they cluster by meaning, syntax, or task labels. 4. Activation attribution. Use techniques like integrated gradients or layer-wise relevance propagation to find which tokens and neurons drive specific outputs. 5th, neuron-level analysis. Identify individual neurons or attention heads that specialize in tasks, e.g., detecting numbers, names, code syntax. Why it matters. Improves trust in debugging. You can see if the model's reasoning aligns with expectations. Helps in model editing or fine-tuning. Targeting the right layers for intervention. Example is in GPT-like models, early layers often encode surface-level token info, middle layers capture syntactic structure, and later layers encode task-specific semantics. Interpreting hidden states confirms this progression. Describe your role in a project using generative AI for medical imaging. In a recent project, our goal was to assist radiologists by using generative AI to enhance and synthesize medical images, particularly MRI scans, for better detection of rare pathologies where training data was scarce. The task is, my role was to lead the design, development, and evaluation of the generative pipeline while ensuring medical accuracy, regulatory compliance, and ethical safeguards. Action. Model design. Chose a conditional GAN plus diffusion hybrid to generate high-resolution MRI slices conditioned on partial or low-quality scans. Data handling worked with anonymized DICOM data under HIPAA and GDPR rules. Implemented strict de-identification and encryption pipelines. Training used progressive training starting with low-resolution reconstructions, moving to full 3D volumes. Added structural similarity, SSIM, and perceptual loss to preserve diagnostic features. Validation. Partnered with radiologists for a blinded study comparing real versus synthetic images. Also performed quantitative checks, PSNR, SSIM, and adversarial testing for hallucinations. Deployment. Integrated into PCNS, picture archiving and communication system, with a clear synthetic watermark and audit logging for traceability. Result. The synthetic data increased training diversity by 35%, improving rare lesion detection recall from 0.72 to 0.89 in the downstream detection model. The radiologist rated synthetic images as diagnostically useful in 92% of cases. Reflection. The key was balancing generative creativity with strict medical fidelity. In healthcare, a visually convincing but clinically wrong pixel is unacceptable. How did you address privacy risks in a user-facing generative application? I approach privacy as an architectural requirement, not an afterthought. First, I run a data protection impact assessment to map what's collected, why, and where it flows. Then I apply data minimization only user-submitted content, no hidden scraping and process on device first, using the cloud only with explicit opt-in. All data is encrypted in transit and at rest, with tenant isolation and region residency. We never train on user data by default. If users opt in, I use differential privacy or synthetic augmentation. Before storage, I run PII detection redaction, store only embeddings for retrieval, and enforce document-level access control. For telemetry, I keep logs privacy safe, no payloads, short retention, automated deletion. Users see clear data use toggles and AI-generated labels, with full control to delete history. This approach passed privacy review on first try, kept 0 PII incidents, and still delivered high model performance through synthetic plus DP training. Share how you manage negative feedback or failure in a generative AI project. In a generative AI chatbot project for customer support, our first beta launch received negative feedback. Users complained about irrelevant answers and a few tone issues that made the bot sound unhelpful. Task. As the lead, my responsibility was to address these failures quickly without losing user trust. Action. Root cause analysis. Reviewed logs. Found the model was hallucinating due to vague prompts and incomplete retrieval data. User feedback loop. Added an in-chat thumbs up, down with comment, capture for targeted retraining. Prompt refinement. Introduce structured, domain-specific prompt templates to reduce ambiguity. RAG improvements expanded the knowledge base, improved document chunking, and tightened retrieval filters. Tone guardrails added a lightweight classifier to detect tone mismatches before responses were sent. Result. Within 4 weeks, irrelevant responses dropped by 63%, CSAT rose by 18 points, and user complaints fell to near zero. The project went from at risk to being rolled out company-wide. What KPIs did you use to measure your model's impact in production? I treat model KPIs as a mix of technical performance, business impact, and user trust metrics. 1. Technical quality accuracy, or recall, or F1, to ensure correctness. Hallucination rate, percent of outputs with factual errors. Latency and throughput, P95/P99 response times, tokens per second. Uptime, SLA compliance. Model availability and production. 2. User experience, CSAT/NPS. Direct user satisfaction. Deflection rate for support bots. Percent of queries resolved without human escalation. Engagement metrics, session length, repeat usage, completion rates. 3. Business value cost per request. Infra plus inference cost per API call. ROI uplift, revenue gain or cost savings versus baseline. Adoption rate, growth in active users after launch. 4th, trust and safety. Toxicity, offensive output rate, tracked via classifiers. Opt-out rate, percent of users disabling AI features. Example is, in a generative search assistant, we tracked answer accuracy, latency, CSAT, and cost per query. By tuning prompts and retrieval, we cut latency by 40% and cost per query by 22%, while accuracy improved 15%, driving a measurable revenue lift. Describe a situation where you had to optimize a generative model for speed and cost. I was leading a generative search assistant project where inference latency averaged 4.5 seconds and compute costs were 30% over budget. Unacceptable for a real-time user experience. Task. My goal was to reduce response time below 2 seconds and bring costs back within target without hurting quality. Action. Model distillation. Trained a smaller student model from the original LLM, preserving performance on key tasks. Prompt optimization, reduced unnecessary context in RAG prompts, cutting token count by approximately 40%. Quantization, used 8-bit inference with minimal accuracy loss. Caching, implemented a semantic cache for repeated queries to skip regeneration. Batching and streaming, batched similar requests in backend and streamed partial outputs to improve perceived speed. Result, latency dropped to 1.7 seconds. P95, infra cost per query fell by 38%, and CSAT improved by 12 points. This optimization allowed us to scale to 5 times more concurrent users without adding GPUs. How do you communicate technical model results to non-technical stakeholders? I focus on translation, visualization, and relevance, making sure the audience gets what matters to them without drowning in math. 1. Translate metrics into impact instead of saying F1 score improved from 0.72 to 0.84. I say, the model now correctly answers 12% more customer questions without human help. Tie precision, recall to business. KP is like revenue, churn, or satisfaction. 2. Visualize the story. Use simple charts, bar, trend, confusion matrix heat maps with clear labels. Show before versus after snapshots. Stakeholders love side-by-side examples of old versus new outputs. 3. Use relatable analogies. For example, explaining recall. It's like a metal detector. The more items it finds, the higher the recall, but we also care about avoiding false alarms. 4. Focus on actionable takeaways. Here's what's working, here's what needs improvement, and here's the business value if we fix it. Example is, when presenting chatbot improvements to execs, I skipped token-level loss curves and instead showed response accuracy, average handle time savings, and cost per query reduction, all tied to quarterly targets. Describe a time you had to work with a cross-functional team in deploying generative AI. I was leading deployment of a generative AI document summarization tool for a legal tech client. The goal was to help lawyers quickly review long contracts while ensuring compliance and accuracy. Task. My role was to coordinate between data scientists, software engineers, legal experts, product managers, and compliance officers to ensure the model was both technically sound and legally safe. Action, alignment workshops. Gathered all teams to define success metrics, accuracy, latency, and compliance thresholds. Domain integration. Worked with legal SMEs to create a domain-specific prompt library and validate outputs. Engineering collaboration. Partnered with back-end engineers to integrate the model into the client's contract management system with secure APIs. Compliance sign-off, implemented audit logging, PII redaction, and disclaimers, reviewed with compliance and legal teams. Iterative testing, ran user acceptance testing with lawyers, incorporating feedback into prompt tuning and retrieval augmentation. Result, the tool reduced average contract review time by 47%, passed a full legal compliance audit, and achieved a 95% adoption rate within 2 months. What challenges did you face in integrating generative AI into a legacy system? I was tasked with integrating a generative AI search assistant into a 12-year-old customer support platform with monolithic architecture and limited API capabilities. Task: my goal was to integrate the AI without disrupting existing workflows, while keeping latency under 2 seconds and ensuring security compliance. Action: system analysis, mapped legacy APIs, data flows, and authentication mechanisms to find integration points. Middleware layer: built a modern API gateway to translate between the AI services REST interface and the legacy SOAP XML calls. Incremental rollout: deployed AI as an optional smart search sidebar first, avoiding full system rewrites. Performance optimization: implemented caching for frequent queries and batch data retrieval to reduce round trips. Security compliance: added encryption, token-based auth, and PII redaction before sending data to the AI model. Fallback logic: ensured if the AI service failed, the system would seamlessly revert to the original search engine. Result: we integrated the AI in under 8 weeks, reduced average query handling time by 32%, and achieved zero downtime during migration. How do you stay updated with the latest research in generative AI? I treat staying updated in generative AI as a structured habit, not a side activity. 1. Research papers and preprints I follow: ARGSHIve, cs.lg, cs.cl, cs.cv, and set up RSS alerts for keywords like diffusion, LLM alignment, and multimodal. I use papers with code to see benchmark results alongside implementations. 2. Conferences and workshops: attend and watch talks from NeurIPS, ICML, ICLR, CVPR, and specialized workshops like Gen AI for healthcare. Review poster sessions and tutorials for emerging techniques. 3. Industry blogs and release notes. Track updates from OpenAI, Anthropic, Google DeepMind, Stability AI, Hugging Face, and Microsoft Research. Subscribe to newsletters like The Batch, Import AI, and Latent Space. 4th, community engagement. Participate in Hugging Face forums, Reddit's ML community, and Discord Slack groups for practitioners. Contribute to open source repos to learn from real-world code bases. 5. Personal experiments. Re-implement new architectures or training tricks on small datasets. This cements understanding beyond just reading. How do you mentor junior teammates on responsible AI practices? I mentor juniors on responsible AI by embedding it into their daily work, not treating it as a one-time training. 1. Start with principles. I introduce core frameworks like fairness, reliability, privacy, safety, transparency, and accountability. Use real-world case studies, e.g., biased facial recognition, toxic text outputs, to show why it matters. 2. Make it hands-on. Pair program on tasks like bias testing, PII detection, or prompt safety tuning. Have them run model audits, measure fairness metrics, and implement content filters. 3. Build it into reviews. During code and model reviews, I ask them to justify data sources, pre-processing choices, and risk mitigations. Encourage documenting assumptions and limitations in model cards. 4. Encourage continuous learning. Share updates from Microsoft Responsible AI Standard, research papers, and incident reports. Have juniors present learnings to the team to reinforce knowledge. 5. Lead by example. I consistently apply these practices in my own work, so it's not do as I say, but do as we do. Result: juniors don't just know the theory. They can identify risks, propose mitigations, and bake responsible AI into every design choice they make. What are some emerging trends in generative AI for 2025? In 2025, generative AI is shifting from flashy prototypes to high-impact, production-ready systems. First, agentic AI is taking off models that can plan, decide, and act across multiple steps, not just generate text or images. Think AI assistants that book travel or manage supply chains autonomously. Second, real-time multimodal generation is emerging. For example, Google DeepMind's Genie 3 can create interactive 3D worlds from a single text prompt, enabling new applications in gaming, training, and simulation. Third, we're seeing AI-driven coding, vibe coding, where developers iteratively guide LLMs to build full applications with minimal manual code. Fourth, there's a focus on sustainable AI, reducing the environmental footprint of large models through efficient architectures and greener infrastructure. Fifth, companies are moving from hype to measurable business value, tracking ROI and productivity gains. Finally, regulation is tightening with frameworks like the EU AI Act. Teams must design for transparency, safety, and auditability from day one. How are GANs, VAEs, and diffusion models converging or evolving? While GANs, VAEs, and diffusion models started as distinct generative paradigms, in 2025 we're seeing them converge and borrow from each other. GANs are evolving beyond pure adversarial training. Hybrid architectures now combine GAN discriminators with diffusion-like denoising to improve stability and fine detail. VAEs are gaining more expressive decoders and perceptual loss functions, closing the quality gap with GANs, and some use score-based or diffusion priors in the latent space for sharper outputs. Diffusion models, now the state-of-the-art in image to video generation, are being accelerated with GAN-style discriminators for fewer sampling steps, or VAE encoders for latent diffusion, which cuts compute costs dramatically. The trend is toward hybrid systems, VAE encoder for compression, diffusion for high-quality synthesis, GAN loss for sharpness and realism. This convergence delivers the best of all worlds: controllability, quality, stability, and efficiency, and is becoming the dominant approach in cutting-edge generative frameworks. What advances are being made in multimodal generative AI? Multimodal generative AI is rapidly advancing in both capability and integration. First, models like OpenAI's GPT-4o, Google Gemini, and DeepMind's Gemini Pro Vision can process and generate text, images, audio, and video in a single architecture, enabling seamless cross-modal reasoning. Second, real-time multimodality is emerging, where the model listens, sees, and responds instantly. For example, generating a narrated image while simultaneously answering questions about it. Third, cross-modal alignment has improved through large-scale contrastive pre-training, e.g. CLIP-like methods, combined with joint embedding spaces, making it possible to translate meaning across text, visuals, and sound with high fidelity. Fourth, we're seeing interactive multimodality, where a user can sketch, speak, and type instructions, and the AI fuses these inputs to refine outputs dynamically. Finally, domain-specific multimodal systems are on the rise, from medical imaging assistants that combine radiology scans with patient notes, to retail AI that pairs product photos with marketing copy generation. In short, multimodal AI in 2025 is moving from static, single-shot generation to dynamic, context-aware, real-time collaboration across media types. Discuss the impact of open-source models on generative AI innovation. Open-source models have massively accelerated generative AI innovation by lowering the barriers to experimentation and deployment. First, they've democratized access. Instead of only big tech having cutting-edge models, frameworks like Stable Diffusion, Llama, Mistral, and Falcon put state-of-the-art capabilities in the hands of startups, researchers, and hobbyists. Second, open models drive rapid iteration. The community can fine-tune, optimize, and adapt them for niche domains far faster than closed teams can. Many breakthroughs like ControlNet for image conditioning or LoRa for efficient fine-tuning emerge from open-source collaboration. Third, they enable transparency and trust. Researchers can inspect architectures, training data sources, and bias profiles to understand limitations and improve safety. Fourth, they spur competitive pressure on closed providers to innovate faster and offer better APIs. However, there's also a responsibility challenge. Open weights can be misused, so the community is developing responsible release strategies, e.g., gated access, model cards, and usage licenses. Net impact. Open source models have transformed generative AI into a global, collaborative R&D lab, multiplying the speed and diversity of innovation. What new ethical challenges are emerging with personalizable generative models? Personalizable generative models, ones that adapt to an individual's style, history, or preferences, unlock powerful experiences, but also introduce new ethical challenges. First, there's privacy risk. Models may store or infer sensitive personal data during fine-tuning or in-context learning. Without strong data minimization and differential privacy, personalization can become inadvertent surveillance. Second, identity manipulation. Hyper-personalized outputs can mimic a person's voice, writing, or likeness so accurately that it risks deepfakes, impersonation, or non-consensual content generation. Third, reinforcement of bias and filter bubbles. Tailoring outputs too closely to a user's preferences can lock them into narrow perspectives, reducing exposure to diverse viewpoints. Fourth, consent and control. Users need transparent settings to decide what data is used, how long it's stored, and the ability to reset their AI profile. Fifth, accountability. When a personalized model makes a harmful suggestion, it can be harder to assign responsibility since the behavior is partly user-driven. In short, personalization increases value, but also magnifies privacy, fairness, and misuse risks, meaning ethical guardrails, transparency, and user control must be built in from day one. How do you debug a generative model that produces poor outputs? I debug poor generations like a doctor. Triage, isolate, fix, verify. 1. Triage and reproduce. Save the failing prompt, seed, decoding parameters, temporary, top p-beam, and model version. Create a minimal failing case and a gold example for side-by-side diffs. Second, classify the failure: factuality, hallucination, style, format, reasoning, toxicity, safety, latency, timeouts. Each class points to different fixes. 3. Input and retrieval checks. For RAG, is the question answerable from the corpus? Check retriever, recall precision chunking and re-ranking. Trim to the most relevant spans. Add source citations. Fourth, prompt and decoding. Add a system contract. Answer only from context, else say I don't know. Enforce structure, schemas, stepwise plan. Tune temperature, top, p, beam. Many bad outputs are decoding issues. Fifth, model ablations. Compare smaller versus larger checkpoint. Try domain-tuned model. For diffusion, adjust steps scheduler guidance. For GANs, watch mode collapse. Use WGAN-GP feature matching. For LLMs, inspect per token logits around wrong turns. Test self-consistency in greater than one samples. Sixth, data and signals. Examine training, fine-tune data for leakage, bias, label noise. Add task-specific exemplars. Consider LoRa, refresh on failure cases. 7. Automated guards. Add claim verification, entailment versus context, format validators, and safety filters. Build a regression suite, prompt tests, so fixed bugs don't return. 8. Verify and monitor rerun offline evals plus online A/B against a known baseline. Track groundedness, accuracy, edit distance, and P95 latency. Walk through your process of deploying a new generative AI capability end to end. I run new generative capabilities like a product launch with guardrails, discovery to design to data, to model to safety, to serving, to launch to learn. First, problem and success criteria. Define the user job to be done, constraints and success metrics, quality, P95 latency, cost or query, CSAT groundedness. Second, risk and privacy by design, DPIA threat model, intended use or abuse cases, data minimization, tenant isolation, region residency, no training on user data, default. Third, data and knowledge grounding. Curate domain corpora, build RAG pipeline, chunking, embeddings, ANN index, re-ranking. Set document ACLs and freshness SLAs. Fourth, model strategy. Choose baseline, closed or open. Plan LoRa Q LoRa, fine-tune if needed. Define prompt templates, tools functions, and decoding defaults, temp top P. 5. Evaluation gates, pre-prod, offline suites, task quality, groundedness hallucination, toxicity, bias, human eval plus gold sets. Ship only if gates pass. 6. Safety stack, pre-filters, PII, secrets, jailbreak. System contract, answer only from context, else abstain. Post filters, toxicity or PII. Citations, watermark content credentials. 7. Serving architecture. Stateless inference behind API gateway. Continuous batching, KV cache, speculative decoding. Tiered models, fast draft to refine. Autoscale with warm pools, edge region routing. 8. Observability and cost control. Trace request to retrieval to prompt to model with correlation IDs. Track P50/P, 95/P99. Tokens per second, cache hit rate, cost per query. Budget guards, rate limits, circuit breakers. 9. Rollout plan, shadow traffic. Internal beta, canary, feature flag, blue-green. Rollback ready. Model/prompt/index versioned in registry with signed artifacts and changelogs. Publish system/model cards. 10th, post-launch learning loop online AB, live groundedness checks, claim verification, edit distance versus user corrections, flagged output triage, weekly prompt/ranker tweaks, monthly safety/red team review. Explain how you benchmark your system against state-of-the-art. I treat benchmarking as a continuous multi-layer process, not a one-time comparison. 1. Define scope and KPIs. I align metrics with the task. Example is blue, rouge, meteor for summarization, FID IS, clip score for image generation, latency cost per query, and groundedness for production systems. Include human eval for subjective quality. 2. Choose baselines. Compare against state-of-the-art open models. Example is Llama, Mistral, SDXL, and closed APIs. Example is GPT-4, Claude, Gemini. Use identical prompts, decoding parameters and constraints to ensure fairness. Third, standard and domain benchmarks run on public benchmarks, MMLU, BIG Bench, HELM for general capabilities. Create domain-specific test suites from real use cases, ensuring coverage of edge cases and failure modes. 4. Statistical rigor use paired tests. Example is Bootstrap t-tests to confirm performance differences are significant. Track confidence intervals, not just point estimates. 5. Continuous tracking. Integrate benchmarks into CI/CD. Every model or prompt change triggers a benchmark run. Maintain a leaderboard dashboard to track drift over time and against new SOTA releases. 6th, interpret and act. If SOTA beats us in certain metrics, I drill into error clusters to guide fine-tuning, retrieval tweaks, or prompt redesign. What is your approach to continuous learning for model improvement? I approach continuous learning as an always-on feedback loop. Collect, curate, adapt, evaluate, and deploy. 1. Feedback ingestion. Capture explicit signals, user ratings, thumbs up, down, comments, and implicit signals. Click-through rates, edits to AI outputs, task completion rates. Flag unsafe or low-quality generations for special handling. 2nd, data curation and labeling. Aggregate feedback into a training queue. Filter for quality, deduplicate, and annotate edge cases. Use active learning to prioritize the most informative examples for labeling. 3rd, model update strategies. For quick wins, apply prompt engineering or retriever tweaks in RAG setups. For deeper fixes, perform LoRa/Q LoRa fine-tunes or reinforcement learning from human feedback/RLAIF on curated examples. 4th, evaluation gates rerun offline benchmarks and human evals before deployment to ensure the change actually improves KPIs and doesn't regress others. 5. Deployment and monitoring. Roll out updates gradually with canary testing. Keep version models so we can roll back instantly if needed. 6. Knowledge base refresh schedule. Periodic corpus updates for retrieval-augmented systems to keep answers current without retraining the whole model. How do you ensure your generative model aligns with product or organizational values? I align generative models with product and organizational values by embedding those values into every phase: design, training, evaluation, and deployment. 1. Translate values into actionable guidelines. Work with product, legal, and ethics teams to turn high-level principles like accuracy, fairness, safety, inclusivity into clear model behavior rules and prohibited behaviors. 2. Bake values into data and prompts. Curate training and fine-tuning data that reflects desired tone, cultural sensitivity, and domain accuracy. Use system prompts and guardrails that set boundaries. Stay grounded in context. Avoid personal opinions. 3. Multi-layered evaluation. Add value alignment tests to offline evaluation suites. An example is bias audits, safety checks, and inclusivity scoring. Include diverse human evaluators to catch cultural or contextual misalignments. 4. Safety and compliance filters. Deploy pre- and post-generation filters for PII, unsafe content, or policy violations. Include fallback behaviors. An example is, "I can't answer that" when out of scope. 5. Continuous monitoring and feedback loops. Track production outputs for violations with an escalation and correction workflow. Regularly review flagged cases with cross-functional teams to refine rules and retrain if needed. What excites you most about the future of generative AI, and where do you want to contribute next? What excites me most about the future of generative AI is its shift from being a tool that creates content to becoming a true collaborator that can reason, plan, and act in the real world. We're moving toward agentic AI systems that combine generation with memory, retrieval, and tool use, enabling them to execute complex, multi-step tasks across domains. This unlocks breakthroughs in personalized education, medical decision support, and creative industries at a scale we've never seen before. I'm particularly excited about multimodal, real-time systems that can understand and generate across text, speech, images, and 3D environments, creating entirely new interaction models between humans and machines. Where I want to contribute next is building safe, grounded, and value-aligned generative systems that solve high-impact problems in healthcare and knowledge work. I want to focus on bridging cutting-edge research and reliable ethical deployment so that these systems are not only powerful, but also trusted and accessible to everyone. How is generative AI used in 3D model or video generation? Generative AI is used in 3D model and video generation by learning patterns from existing spatial or temporal data and synthesizing new, realistic assets that match a desired style, scene, or motion. For 3D model generation, common approaches include voxel-based models, generate 3D objects as volumetric grids; point cloud generation, use generative models, like PointNet-based GANs or VARIs, to produce 3D shapes from scratch; neural radiance fields, NeRFs, learn a continuous 3D scene representation from 2D images, allowing new viewpoints to be rendered realistically; text to 3D pipelines, combine language models with diffusion models like Dream Fusion to generate 3D assets directly from natural language descriptions. For video generation, generative AI models extend image synthesis into the temporal domain. Autoregressive video transformers predict the next frame conditioned on previous ones. Diffusion-based video models apply denoising steps in both spatial and temporal dimensions. GAN-based video synthesis use temporal discriminators to maintain motion realism and frame-to-frame consistency. Applications include creating game assets, virtual reality environments, cinematic previsualization, simulation data for robotics, and video effects. The key challenges are maintaining spatial realism, temporal coherence, and controllability over camera angles, lighting, and object motion. You've done it. 100 generative AI interview questions mastered. This is more than preparation. This is transformation. With every answer, you've built the skills, the confidence, and the mindset to step into your interview ready to win. But the journey doesn't stop here. In our next series, we'll unlock the top 50 RAG interview questions, the key to mastering retrieval-augmented generation, one of the most in-demand skills in AI today. Subscribe now and keep moving forward, and because your future in AI is just beginning.